right? If you get that, you're done. You move on to the next problem, right? So that means I'm going to want drawings. I'm going to want things to support your formulas. All right, so I'm going to use vertical rectangles, right? I'm going to use vertical rectangles because these are functions of x, so it makes sense to use a vertical rectangle. I notice that my rectangle is orthogonal or perpendicular to my axis of rotation, which means I want to use shells. I mean, God damn it, Robert. Washers. I just feel like I need to walk out and come back in. Washers, which is what I've shown you here, right? Shells is next. So there. Orthogonal washers. So let's move this over. I always like to move this to the side over here. This is not a necessary step, but I always like to move it to the side and kind of like just get rid of all the clutter so I can see everything kind of like this. So I've got my blue curve on top. I've got my red one on the bottom. And now I wrap this thing. So when I wrap it, right, when I wrap it to create this washer, it's going to be pretty big, right? It's going to be like this. That's my washer there. It's not perfect by any means. There are only two things you need for this formula. Well, two to set up the integral. You also need the limits of integration, but I think we're okay with that here, aren't we? We already know it's 0 to 1. All we need is the outer and inner radius, and we're in business. So the outer radius is if you read it, the outer radius is the distance from what? The axis of rotation to the outer edge of the rectangle, right? From here to here. That distance is what we're looking for. So I always like to envision it like if I was physically standing on this dotted line looking out. So like if this was a dotted line and I look out, see a rectangle on the floor over there, right? I'm standing here, I'm looking for that outer edge of that rectangle. And that for us would be here, right? That distance we need to know. It's not x, is it? It's not x. Because x goes from what? From here to here is x, isn't it? That's x. That's that function, the blue function. But then we have an additional how much? Look at it as a distance, like measuring tape. If I was going from here to there, that would be, well, -4 is, it's -4 down from the x-axis, but as far as a distance, it's what? 4. Right? 4. So what is this total distance from here to here? X plus 4. X plus 4 is your total outer radius. So that's RO. Questions on RO? Sure? Yes?
So for all the rectangles that are drawn, are they all going to be x because y is equal to x?
Are they all going to be x? I'm not sure what you mean. For this?
Yes, so let's say you had like a different rectangle within under the curve. Are they all going to be equal to x?
No, the only reason I'm putting x here is because that's the top function. If this happened to be like maybe the sine function, if that was sine x, the one on top, then this would be sine x. Yeah, the top function dictates this. This distance is dictated by the blue function. Okay? Is that good? Everyone else? Anyone else? So we're all good on where our out comes from, outer radius. Now we need the inner radius. What's the inner radius? It's the distance from the axis of rotation to the inner edge of the rectangle, from here to here. So Rn is that, which again is not just the red curve, right? The red curve goes from here to here, right? That's x squared. That's x squared there, right? But you need the additional what? 4, right? So from here to here is the x squared plus another 4. So our inner is the x squared plus 4. And once you have that, you should be able to set up the integral as long as I don't screw up and forget the squared again. I'm just going to put here 0 to 1. The limits of integration, remember, the importance of the limits of integration is it's telling you where your rectangles are going to start and where they're going to stop. And your rectangles are actually going to be generating your washers, right? So it's really where your washers start and stop. You ready for the integral? Set it up. Okay, I'm going to use that formula. The volume will be pi integral 0 to 1. Okay, outer radius, x plus 4, squared, right? Minus inner radius, x squared plus 4 squared dx. There we go. Squared. Can you handle that integral? Could you square this? Foil it out? Square that, foil it out, combine like terms, integrate, power rule on each one, nothing crazy, no integration by parts, no trig integrals, like that's just easy power rule stuff, right? Polynomials. And we could get some numerical answer. Okay? All right, let's do the same problem. I'm going to give you a different axis of rotation. This time, the line's going to be above it. Let's see how that changes things. So let's change this. I could use positive 4, but I'm going to just go with 7, just so we have a different number. So I want to now find the volume if it's rotated about y equals 7. By inspection, if you're trying to figure out where those two hit each other, right? It was more of an inspection thing. 0 and 1 are the two solutions. And then also just off of the graph. So you find the intersection of the two. All right, so go a little faster here, hopefully. Let's see, because y equals 7 is above, I'm going to draw it this way. I've got my x here. It's y equals x. Got my x squared here. I've got my axis of rotation way up here at 7. I'm going to use vertical rectangles because these are both functions of x. Vertical rectangle, orthogonal or perpendicular to my axis of rotation means I'm going to use washers, right? I'm going to imagine rotating this around this way. So when I go and I move everything over here to draw my other picture, want me to slow down? Okay. When I draw my other picture over here that I'm going to rotate, I only bring the x-axis, I bring the rectangle, and I bring the axis of rotation over. So I have my x-axis here, I have my rectangle here, and I have my axis of rotation up here. I also like to kind of remind myself blue here, red here. I know when you're working you don't have all the colors, although some of you might. You do this enough times and you don't need the picture, all right? But you have to get comfortable with it first. All right. We only need two things because we already know the limits are from 0 to 1, right? We only need two things, outer and inner radius. The outer radius is the distance from the axis of rotation to the outer edge. So you're standing on the axis of rotation, you see the rectangle on the ground, and you're looking at the edge furthest away from you. So if I was standing right here, looking at the rectangle on the ground, which color edge is the edge furthest away from me? The red edge, right? The red edge is the one furthest away from me. So our outer is actually distance from here to here. That's our outer. See, it's different this time because of where my axis of rotation is. My inner radius is from the axis of rotation to the inner edge, right, of that rectangle relative to me at the axis of rotation. Let's figure out what those distances are. So let's try and find our out. What's that?
X equals 7.
So this right here is x squared, right? From here to here? That's x squared. Everyone agree? That's x squared. So our outer radius for us is this distance, right? Okay, what is this distance from here to here? What's that distance? 7, and that's never changing, right? From here to here is 7. And so how much am I taking away from that? So I'm subtracting that much from that 7, right? So you have to realize here that, I'll do it out here, that from here to here is always fixed at 7 because that's my axis rotation line is way up there, fixed. So if this whole distance is 7, and I take away the x squared, that will leave me with r naught. So what is r naught? 7 minus x squared. It's that total distance from here to here, 7, take away the x squared. And then the inner, it's kind of the same concept, isn't it? We know the distance from here to here is x, right? That's x. And so we don't want that whole distance 7. We want the 7 and take away from it that much, x. So it would be 7 take away x. Do y'all see how this is different depending on where the axis of rotation is? Yes?
So when we're doing the x and the x squared, because you're kind of losing me there, is that just like the original equation
Yeah.
in relation to the x-axis?
Yes, that's exactly what it is. Because remember, look, this is x, right? This is x squared. So when you're looking at that rectangle over here, remember, the x graph goes like this, and the x squared comes up like this, but it's too much clutter if I try and draw them all together. So you just have to remember that that blue edge, what dictates this top edge of the rectangle? No matter where that rectangle is, right? No matter where it is, what's the top edge? Y equals x. So as you move around, this r inner will always be dictated by this height right here. It'll be 7, take away that much, right? And that's x. Now the bottom edge is always the red one, right? And that distance is always x squared. So this outer radius is always dictated by that x squared, has to be subtracted from 7 as you move across. Does that help at all or no?
Yeah, I guess I was just confused because somehow, like, to me in this perspective, somehow x looks like it's bigger than x squared. So, but
It is, but because, remember, we are between 0 and 1. That's what I was just saying a second ago. Between 0 and 1, x is bigger than x squared.
Oh, okay.
Right? If you graph them, x is like this, x squared's below it, because when you square a number between 0 and 1, it gets smaller.
Okay.
Maybe that's where the disconnect was. You're like, wait a minute, x squared should be above x. As soon as you get past 1, then yes, the parabola is above the line.
Okay.
Any other questions?
So would you say that you can always be subtracting?
So in my experience with this, students who try and memorize cases this doesn't go well. You have to understand the geometry of what's happening. Because we've only done 3 cases. There's another 3 we have to look at where we're wrapping this way. And if there was something where I could tell you it's always this, then I would probably teach it that way. But you really have to understand the geometry. That's just my opinion. Because you were going to say something like, if the axis is up here, then you're just going to subtract or something like that?
If it's on the same side of the x-axis.
If it's on the same side. What do you mean? I'm lost now.
So for the previous example, the rectangle
Uh-huh.
was on the opposite side of the x-axis.
That's right.
Then the axis of rotation. And for that one, we had to add it because we had to add the
Yeah, we had to add that distance to that height, right?
So when it's on the same side, because it's on the same side, and there's going to be that little difference between them, that's where we subtract.
I'm going to just say yes in this example.
Okay?
Okay, I don't want to generalize it because there's danger. What if this graph is in this quadrant? Like down here, not up here? Where's your axis of rotation? Like, you have to understand how to generate the formula from the geometry you have. If you just look at, like, okay, if it's above, I do this, if it's below, I do that, it's gonna catch you. I think you'll get. I think it's from the geometry of you have where your rectangle's at, right? Where are they? Where's your axis of rotation? Okay, in that case, figure out what the outer and inner radius are. It's a relative position from here to the outer, from here to the inner. What is that geometrically? Every problem is somewhat unique. Now, I'm not going to try and like trick you, okay, on a test, but I do want you to understand the geometry. Let's get a final answer. Yes? The volume of this thing will be pi, because the formula always has a pi, integral 0 to 1, because that's what we said, that's where it starts and stops for this region. And then I'm going to have, I know I'm going to have a lot of stuff in here, dx at the end. Outer radius squared, 7 minus x squared squared minus inner radius, which is 7 minus x squared. See, and I'm not forgetting the squareds this time. I have this idea that when I die, I'm going to go to some place where I'm going to get lashings for all of the mistakes I made in class. Remember this one? Remember, it's like a purgatory for a math purgatory. Square it, damn it. All right, we good? I'm conflicted here on what I want to do here. I want to do a really cool example. I'm going to do the examples, I think. I think that's what I want to do. Okay. So I'm not telling you right now to completely forget this, okay? Don't forget it completely. This is it. This is washers, right? Now there's another method called shells that we'll do next class, right? And that's how we wrap the other way around a vertical line instead of a horizontal line. And I haven't even talked about what happens if this region, what if these aren't functions of x? What if these are functions of y? And we want to wrap around, like what if I give you a function of y here and you want to wrap it around? You're going to have a problem because your rectangles can't be vertical anymore. They have to be horizontal. And that's an issue. I haven't shown you how to do that yet, right? So I'm going to show that to you. You just have to be here next time. All right, so I have two examples. Let's kind of like open up our thinking here, not get fixated on just this idea. I want you to think of everything we've talked about in chapter 7. And I'm going to get rid of that because I want the whole board for this. All right, 2 problems. Let's see if I can do 2 problems in 15 minutes. It's going to be a stretch. All right. I want to do this one first. I'm going to go in backwards order. Prove the volume of a sphere is a sphere radius 9 of radius capital R is, what is the volume of a sphere or a ball of radius 9? Anyone know what the formula is for it? 4/3 pi r cubed. Prove it. And that's a formula we can look up, right? It's in our formula sheet. It's prove that the volume of a sphere of radius r, capital R, is 4/3 pi r cubed, right? So in other words, where did this formula come from is what we're about to answer, right? And we're going to use exactly what we just learned today, right? So the first thing I'm going to do, and we did something similar to this before. Do y'all remember when we proved that the area of a circle of capital R was equal to pi r squared? Remember we proved area? And to do that, what we did was we drew a half circle. So you have to go back in your notes. And what we showed is that that circle has as an equation y equals the square root of capital R squared minus x squared. It came from the idea that a circle centered at the origin, if you center a circle at the origin, here's the equation of that circle. X squared plus y squared equals capital R squared. If you solve this for y, you wind up getting a plus or minus on this. And then the positive one draws the top half and the negative one draws the bottom. Does that ring a bell? Because we did do that before. See some nodding, yes? Okay, so this is actually the top half, right, of a circle. We want to prove that the volume of a sphere of radius r has this volume. Do you all see that if I take just this, I guess I could take the whole thing, but let's just look at that first quadrant. If I take just that region and wrap it around the x-axis, I'll get half the ball, right? And I should be able to find the volume of half the ball, and then I can just double that answer, and that would give me the whole ball. Yeah? Okay, so this is it right here. This is exactly what we just did just a second ago. I have on top, right, I have this curve. Now, on the bottom, I need a function on the bottom, right, for an inner radius. Do y'all see, since I'm wrapping around the x-axis, my bottom function is just y equals 0? And then I'm just going to take my rectangle. Imagine my rectangle's in here, right? They can be anywhere in here. And I'm just going to wrap those around. And I'm going to get washers, but do y'all see these washers don't have any holes in the washers? Right? It's just solid washers the whole way, like discs, right? All right, so if I draw over here, my axis of rotation is actually the x-axis. Let me draw my rectangle here. I have the blue on top. I have the red on the bottom. But this is also where my x-axis is. But this is also where my axis of rotation is. Is that too much? Do you all understand that? I didn't draw it, but I'll draw it over here. I'm hoping that everyone sees that if I wrap that whole region around, I get like that, right? Like the half of it. And then I'll just double this answer. So R out is the distance from the axis of rotation to the outer edge. That's R out. And R in is from the axis of rotation to the inner edge. What's that going to be for us? 0. The inner radius is going to be 0. But what's R out? It's just that, isn't it? Square root of capital R squared minus x squared, right? It's just that blue curve, which is that function. Any questions? No? Okay, so if that's what we've got, I think we don't need, we need to know where we're going to start and stop. Okay, so where are we going to start? We've chosen to start where? 0, and where are we going to stop? Capital R, right? We're going to go from 0 to capital R. I'm doing it. Here we go. The volume of this thing should be pi, why pi? Because the formula involves pi, right? Integral from 0 to capital R. All right. I know I have dx back there. Outer radius squared. The square root of r squared minus x squared, that thing squared, minus the inner radius. What was our inner radius? 0, but then squared. Oh my God, that's awesome. Do you see that when we square the square root, it goes away? And that's 0. So this is just pi integral from 0 to capital R of capital R squared minus x squared. That's it? Right? That's it? That's all I have to do? Now, capital R is a constant, right? It's a fixed radius. So this is a constant, and this is just x squared. Can you integrate x squared with respect to x? 1/3 x cubed. Can you integrate a constant? What's the antiderivative of, let's say, 5? 5x. What's the antiderivative of 10? 10x, right? What's the antiderivative of r squared? R squared x. R squared x.
R squared x or RX squared?
R squared x. Because it's a constant, right? Like I'm saying, whatever this number is, say that number is 4, right? What's the antiderivative of 4? 4x. Let's say that number is 100. What's the antiderivative of 100? 100x, right? Y'all are looking, some of y'all are like, yeah, yeah, and others are like I equals, here comes the antiderivative. Pi is coming for the ride. The antiderivative of r squared, capital R squared, is r squared x, right? And then minus the antiderivative of x squared, which is 1/3 x cubed, right? That's my antiderivative. We're using the fundamental theorem of calculus, so we do the evaluation bar, we're going from 0 to capital R. I'm going to come back over here. So now this equals, all right, we got to plug in two different things, right? All right, let's plug in capital R first, okay? Capital R first. I'm going to have a pi. Okay, when I plug in capital R right here for x, what do I get? Capital R squared times capital R? R cubed. Okay, minus 1/3, and then 1/3, and then what? R cubed again. Okay, that's when I close the parentheses off right there. Now let's plug in 0 for x. Well, that's nice, isn't it? 0 here, 0 here, pi times 0 is 0. It kills everything off here. I just get 0. And so I have here, let's see, pi. What happens if you take 1 r cubed and you take away 1/3 r cubed? You get 2/3 r cubed. 2/3 capital R cubed. And now what you can do is you can put this in it, kind of make it look a little different. You can go 2/3 out front, then you can go pi and then capital R cubed, right? That would be the volume of this, right? And now you just double it because you want the other part, right? If you double that, what do you get? 4/3 pi R cubed. You see? Pretty cool, right? Not that hard, actually. When you think about it, like our integration, if you go back in your notes when we proved that the area of a circle is pi r squared, it was harder than this because we had to do trig sub. We had to actually, the integral required trigonometric substitution. This integral is actually easier. It's easier to show the volume of a sphere is 4/3 pi r cubed than it is to show that the area of a circle is pi r squared, right? But we still did it, and we're all happy about it. Okay, so here's what, let's do this. Give me a second here. We still have 5 minutes. I want to give you a homework assignment, but here's what I'm thinking I'm going to do. So this is a problem directly from an exam review. So you can either take a picture of this or write it down, but I give you 3 curves. Let me get in here first and explain, and then you can take a picture. So it says set up the integrals, but do not evaluate. So in other words, just set them up, get the formulas, which give the volume of the solid form by revolving the region bounded by these things about the x-axis, y equals -3, y equals 4, the y-axis, x is 5, x is 3. We haven't done these, okay? So just do A, B, and C for that. Try that for a take-home quiz. How about that? all right? And then also you'll want to start doing your homework for this section, all right? I'm going to have to look to see exactly what problems, but 7.1 now, you should be able to do all the homework in 7.1. I'll send you an email. I promise this time I will do it. I'll send you an email that tells you what problems in 7.2 to do. But this is a take-home quiz, right? To be turned in next time, along with, boy, you have a lot of things for next time, don't you? Test corrections, right, next time. This quiz, and the bonus if you want to do it, all right? Remember, only do parts A, B, and C. Don't do D, E, and F, just A, B, and C. All right, everyone. Have a good rest of your day.